Okay, so we're talking about rates of change, and I find this paragraph a really, really important way to explain why rates of change are important. Basically, you know, calculus is a set of techniques to describe the way things move, whether it's planets, space shuttles, ballistic missiles, electricity, radio waves, stock market prices, blood. So it applies in so many different areas, and the common thread to all of these areas is the rate of change of something, whether it's the rate of change of electricity or the stock market prices, etc. So today we're going to try to tackle that concept. How do we find the rate of change of something? And I found also this from another textbook, from Stewart, author textbook. They even mention it's used in meteorology to see the rate of change of atmospheric pressure, or in psychology, the rate of which performance improves. In sociology, the rate at which rumors spread. So it's like the list goes on and on. So the rate of change is a very important concept in many different sciences. And it's really interesting that just one single mathematical concept known as the derivative will solve all of those cases. So we're going to begin with what we already know, and you have a handout today, so you have parts of this, especially the theory portion, already there. So I'm going to go step by step, so let me cover the part I don't need. Okay, we're going to start with what we already know, which is from algebra, we know how to find the average rate of change of a function. But today we're trying to find the instantaneous rate of change. So that's the goal today, the instantaneous rate of change at a given moment. Now, how do we find average rate of change? There's a very simple formula for that. Basically, if you're trying to find the average rate of change of this function over the interval from a to b, it's as if you were finding the slope of this line. Because what would be the slope of that line? It's rise over run, correct? What is rise here? What is this distance? Suppose this function, let me use another color there. Say this function given in green is your y equals f of x function. And we're trying to find its average rate of change over the interval from a to b. It's as if you're finding the slope of that line given in blue. What is the height? What is the rise there? F of b minus f of a, right? And what is the run? That's b minus a. So if we take the ratio of rise over run, which is what you have over here, f of b minus f of a divided by b minus a, this is a very simple formula from algebra, slope. And mathematicians knew this for a very long time. So this was not a problem. We already know average rate of change. And it also translates to be the slope of the secant line. And what is the secant line? Basically the line that joins those 2 points that are separated from a to b. OK, so that is nothing new. This is just a review concept, average rate of change. Let's just see what it means in terms of a context. Say you have y equals s of t, the distance function. What would be the rate of change of distance per unit of time? Any thoughts? The rate of change of distance per time. Say distance maybe is in miles. Time, let's say, is in hours. Distance per time is like mile per hour. What does that represent? Distance per time. Mile per hour, what kind of quantity does that represent? Speed, right? Speed in math, we are more specifically say velocity because it could also indicate direction. But miles per hour represents velocity. So distance per time. So say that we have a distance function s of t, and here I have a graph for that. This should also be in your handout. So let's say that this is the distance function. So this object, after 1 second, it was started moving. It took 20 feet from where it started originally. Then after 3 seconds, it was at 50 feet from the original position. So I want to know, what is the average rate of change of this function? What is the average velocity for the function whose picture we see over here? How can we determine it? Basically, draw your secant line, right? And do rise over run. So this object moved how many feet during that time interval? Right, so this is the secant line, so we're going to rise over run. This distance is 30, right? And how many seconds elapsed in that time? 2 seconds, difference between 3 minus 1. So the average rate of change is going to be what then? Rise over run 30 over 2, or 15 feet per second, right? That's what we have in our notes as well. So average rate of change over the interval from 1 to 3 is rise over run, which is, it can be represented as, since this is a function s of t, it's like s of 3. That means the position at the third second minus s of 1, the position at the first second, divided by the difference time increment, which was 2 seconds. And that gives us 15, basically, feet per second. Okay. Now, the question is, okay, so we already know these things. We're reviewing them. Average rate of change is nothing new. It's the average. It's the slope of a secant line. But the question that troubled mathematicians was, how do you find the instantaneous rate of change, let's say exactly at the point 3? So what you can do then is you can say, okay, we're going to find, actually, in our next slide, before I state it, let me just pull that up here. Here is the idea for the instantaneous rate of change. Basically, make the time increments smaller and smaller. I mentioned to you in our first class, this is something that you and I could have come up with if we just thought a little bit deeply, but such is the case with all the big mathematical ideas. Somebody came up with this and said, why don't we let the delta t, the time increment, approach to 0? Take a limit as delta t goes to 0. So for example, if you're trying to find the velocity at exactly the third second, let's say we have this function. This is the distance function. S of t equals negative 16t squared plus 500. Is there anybody who's taken physics in this class? Anybody who's taken physics? Do you recognize this formula? Like, it represents distance from the ground at any given moment t, and initial velocity is 0, it's free fall, it's been dropped, and initial height is 500. But you don't have to know any of that in math. I don't assume that you know physics. I just give you an equation. S of t, just know that that is the distance equation. That is the distance from the ground at any moment t, okay? Now that we know the distance equation, can we determine the exact velocity, instantaneous rate of change, exactly at the third second? And here's the idea. First, we're going to find the average rate of change. Look at the table of values here, between 3 and 3.5 seconds. We know how to find average rate of change, right? That's the slope of the secant line, right? Okay, then can we find the average rate of change between 3 and 3.4 seconds? Sure, we can apply the same formula to these two numbers, right? Can we do it between 3 and 3.3? You get the idea, right? Go all the way down. Can we do it between 3 and 3.01? We can make it as small as we like, and the closer you get to 3, the closer you're going to have the actual instantaneous velocity at that moment. And in the limiting case, as delta t goes to 0, you have the exact velocity. Okay? So first, we're starting with a table of values, also known as a numerical approach. By the end of the class today, we're going to have an analytical approach that you don't have to look at a table of values. You can find the instantaneous velocity by just manipulating x's and y's. Okay? But right now, just let's get an idea. What is instantaneous velocity at 3 seconds by filling these values? And to save time, I'm going to split the class into groups. Let's say this first row, would you please work on the first case, between 3 and 3.5 seconds. The second row, would you please work on 3 and 3.4 seconds. Next one, 3 and 3.3, 3 and 3.2, 3 and 3.1. And the last one, would you please work on 3 and 3.01. And before you start, let me make sure I explain what we're doing. So this is the average velocity formula from the previous page, right? If you go back, this was our average velocity formula, f of b minus f of a over b minus a. But here the function is s of, the function s, so s of b minus s of a. For example, for the first one, you know your function, right? The easiest way is enter this into your y equals screen. And you can go to the table and you can enter, like, your b is 3.5 seconds for the first group, and your a is 3 seconds. You can quickly get s of b and s of a from your table, and then you can form this ratio. So I'm going to give you a little bit of time. I'm going to pause the recording and then come back and we'll get your answers. Okay, so we spent some time trying to figure it out. So for the first one, it was s of 3.5 minus s of 3 divided by 3.5 minus 3, or half a second. In that half a second, you find how much it traveled, and you take the ratio to see the velocity, the rate of change of distance per time. And what did you guys get for that? Negative something. Negative 104 point, just exactly 104. Okay, very good. 104 feet per second. Okay, for the next group, what did you guys get? Negative 102.4. Would everybody agree in that group? How did you do it? You do s of 3.4, plug in 3.4 in your function, right? Minus, plug in 3 into your function, divided by 3.4 minus 3 seconds or 0.4 seconds. That will give you the answer. Okay, the next group. Christine, what'd you get? I hear negative 100.8. Would everybody in that group agree? Okay, very good. The next one. Negative 99.2. Would everybody agree there with that number? More or less? Okay, good. The next one, 3 to 3.1. Negative 97.6. Thank you. And the last group, did we get anything? Good. Negative 96 point something. Points what? Exactly 96. Okay. So if we were looking at these numbers, where do they seem to be approaching? Where do these numbers appear to be approaching as we get closer and closer to 3? They seem to be approaching to negative 96 feet per second, right? At the end of the class today, we're going to confirm that analytically. We're going to see if that's the exact velocity at the 3rd second. And let me just keep you in suspense. Let me not say what the answer will be, but it's going to be something very, very close to that, to say the least. Okay. So any questions about what we have? Yes, Daniel? Okay, make sure you put the incorrect order in the numerator. If you got positive results, remember, like your case was 3.1 seconds, right? So first, what was S of 3.1 for you? 653.7. Okay, minus, you want to subtract S of 3 now? Yeah, I did that. All right, the initial equation is a negative 16t squared. If you didn't see that, yes, that's probably why you did not get it. Yes, yes. Another question, yes. Okay, the initial equation is a negative because this object was dropped from a top of a building, and it's going downwards. So basically, after each time goes by, the distance is going down and down and down. This object is going downwards, basically. That, again, that goes into a little bit physics aspect of it. But if you're trying to understand the equation, that's why there was a negative. And why was there a 16? Because that's the gravitational constant. It's basically negative. It's like there's a formula, negative 1/2 gt squared. And that's where it's coming from. G is negative 32. But again, we don't have to know any of that. We can still find average rate of change by just following the average rate of change formula, which is this one right here. Okay, so we have an idea. Now, mathematicians are never satisfied with numerical methods. They want an exact, they want an analytical. And you know, although this is a good idea, this is just the introduction to the idea. But to do it for real, in a mathematical, the rigorous way, we got to look into some equations, okay? So what we're going to then look at is, in general, forget about the S of t function, because remember, this doesn't have to be velocity. It could be the rate of change of blood flowing in the body. It could be the rate of change of profit function. So we don't want to restrict ourselves to just one kind of a function. So let's just say y equals f of x. Mathematicians' beloved function notation, right? It applies to any function, y equals f of x. So consider this blue curve in this situation here. That's our y equals f of x. It could be any function. It could be electron flow or anything. Okay? Now suppose that we want to know the exact velocity or exact rate of change at the point P. So let's say that we want to know it right at this point, at the point P. What happened there? Okay. What we're going to do is what we just did already. That was like warm-up exercise in a sense. We're going to start at Q. Draw the line between P and Q. Find the average rate of change. Keep moving. Now from Q, go down to the next point over here. Find the rate of, draw the secant line there, and then find the average rate of change. Then move further to over here. Find the average rate of change. You get the idea. We're going to move as close as we can to P, and eventually those slopes are going to give us the exact slope of the tangent line in the limiting case, right? So if you look at the descriptions down below on that sheet, it starts us with, okay, to find the instantaneous rate of change at a given point, we're going to find the limits of the slopes of the secant lines. All those lines we see up to the red one were the secant lines. As Q moves towards P, that will be the slope of the tangent line. So if we can find the slope of the tangent line at P, that will be finding the instantaneous rate of change at that point. Okay, so that's what we're looking for. If we can answer that question, we've answered the instantaneous rate of change question. Now, there are a few nice little graphs I found online. I want to show you those. Excuse me, not that one. Let's see if I can quickly activate them. Okay. This one is showing the tangent line. You see, as you zoom in further and further and further, that basically the tangent line becomes, if you were able to zoom in further, it will become the same as the curve there. So the tangent line really approximates that curve really well. And we know how to deal with lines. So we can find the tangent line. And by finding the slope of the tangent, we will know the slope of the curve or the instantaneous rate of change at that moment. So again, it's zooming in further and further. You can see the curve becomes a tangent line at a very local zoom in point of view. And also there's another one I want to show, which is this one. This one is going to show us the secant lines. As the secant line moves closer and closer to that point, you see it ends up being the tangent line. The secant lines are approaching. We end up with a tangent line. Now, we know how to handle the secant lines. That's what you did in your cases. 3 and 3.5 seconds, 3 and 3.1 seconds. You are finding the slope of the secant line in every case, okay? But we're trying to find what happens in general without having to do a numerical table. But one thing is for sure. If you start, wherever point you start, you're getting closer and closer. So that increment along the x-axis is going towards 0. So we're going to take a limit as that increment goes towards 0. Okay, so how do you do this as an equation? And here's how we do it. Let me cover it up a little bit. Okay, so we're going to do it very general, not for a distance function, not for a, electron transfer or blood fusion. We're just doing it for one general function, f of x, then it's going to apply to all these different areas. And in the example we worked a few moments ago, we had the time x's on the bottom, right? Here we're just calling the abstract notation x. And what we have is we have 2 points. This is the point P, and this is the point Q. We're trying to find the instantaneous rate of change of this function right at this point right here. So the first idea is you draw this line and you find the slope of the secant line. So what is the slope of the secant line going to be here? Let me use a different color there. So this is our secant line. And I'm going to do rise over run for the secant line. Okay, what is going to be my rise, which is this distance over here? Let's see, is this also in your handout, this slide? Okay, this is the last one. So, right, this one you don't have, so you can copy this one, okay? As a matter of fact, right now, don't worry about copying. Let's try to follow it. And then later on, I'm going to give you some time to write the important part down. But right now, please, let's try to understand. What is that distance, the height, the rise? Very good. F of x plus h minus f of x. Because this is this distance, right? Difference between top minus bottom, right? Okay. And what is this distance over here? Right. And what is that difference? They want how many units? H units. And sometimes some books will use delta x for that, okay? Small incremental distance in x. I'm trying to make the notation simpler for you. I'm using h, but just know that sometimes they will use delta x. Okay, so that means rise over run will be the ratio, f of x plus h minus f of x all over h, right? And what do I need to do to this to get the velocity or instantaneous rate of change at p? I got to take the limit of this as what goes to where? As q is coming down on that curve, what is happening to h or delta x? This point is getting closer and closer, so h is approaching towards 0, right? So what should we do? We should take a limit as what? As h approaches to 0. So if you do that, you will find the instantaneous rate of change of the function. All we have to do is take a limit of the above quantity. This is what mathematicians did not have for so many years. They didn't have the limit concept until Newton and Leibniz in 1600s or early 1700s. That little difference, that limit there, as h goes to 0, it represents that movement that the point q is approaching p, and it gives you the instantaneous velocity at that point. And in the example that we did, earlier, we did that numerically by letting that delta t was like first half a second, then 0.4 seconds, then 0.2 seconds. In the example you did, that increment got smaller and smaller. There we did it numerically, but now we're trying to do it analytically. And this is the part I would like for you to write down, just this part right here, because this we're going to use over and over. The instantaneous rate of change of f of x. As a matter of fact, don't even write this part. I'm going to delete that. It's not necessarily in that. So the instantaneous rate of change of f of x at the point P is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Had we seen that before, maybe in pre-calculus or something, that quotient? We call it the difference quotient, right? But there we didn't associate any meanings to it. But in calculus, it has a very special meaning. It's like the building block of calculus. It's the most important definition, perhaps, the definition of what we call the derivative of the function f. The derivative represents the instantaneous rate of change at a given moment. And I want you to memorize this because this is going to keep coming the entire calculus sequence as of this day and forward. So just make sure that you know. And this notation, you see the prime, f prime of x? F prime represents the instantaneous rate of change, also known as the derivative of f at the point x, okay? So f prime of x is a shortcut notation to represent this, this long expression, limit as h goes to 0, etc. Okay, how do we work with this? How do we use this to come up with instantaneous rate of change? Well, we'll do some examples about that. Anybody who needs more time to copy this formula? Everybody got that? Okay, so let's do an example. We're going to do a very simple example here. So we want to find the equation of the tangent line. First of all, the slope of the tangent line, also known as the instantaneous rate of change of the function at the moment x equals 1. Okay, at the moment, forget about the 1. Let's just apply the definition we just learned, the analytical way of finding rate of change. The definition goes like this. Limits as h goes to 0. Again, this is something that everybody should be very familiar with. F of x plus h minus f of x all over h. Remember, instead of h, your textbook is using delta x, still the same thing. H is a very small increment in the x direction. That's what it represents, okay? So for this function, and notice something I'm going to do here. Every step of the way, I'm going to rewrite the limit notation, because if you don't put the limit notation, what do you have? You don't have the instantaneous velocity, but what do you have without the limit there? You have the average velocity between x and x plus h. We don't want average anymore. That's algebra. We're in calculus. We want to do now instantaneous rate of change. Okay, so for that, let's decide what is f of x plus h for this given function. What will it be? Take the x out, right? And replace the x with what? Replace it with x plus h. That's what f of x plus h is, right? If I want to know what f of a was, how would you do that? You would plug in a for x, right? If I want to know what is f of b, you would plug in b for x. If I want to know f of x plus h, the input should be x plus h, and the output would be x plus h quantity square. Okay, minus f of x. Here you just subtract the same exact function divided by h. Let's simplify this. And what can I do to simplify it? FOIL it, sure, let's do that. X squared plus what? 2xh plus h squared minus x squared all over h. At this point, you will always have simplifications, so the x squareds can be canceled. Now, if I was to plug in 0 for h, I'm going to have 0 over 0 right now. I got to do something to simplify the situation. And this actually explains, excuse me, this explains why we studied limits before derivatives. Because you see, in the definition of a derivative, we have to know about limits, basically. Okay? So what should I do? I have 0 over 0. Well, how can I simplify it further? Yes, Daniel? Exactly. Let's pull it out. Let's factor out an h. Now let's cancel the h's. And what can I do further? I'm taking a limit as h goes to 0. So what can I do right now? Plug it in at this point. We got rid of the indeterminate form. We have 2x. So what we're seeing is something really, really powerful. We're saying that the derivative of x squared is 2x at any given moment. So if you want to know the instantaneous rate of change at the third, second, or x equals to 3, plug in a 3 in here. If you want to know the instantaneous rate of change at 1, plug in a 1 in here. This is giving you the general pattern for any moment in x, okay? And now we're going to do x equals 1. So go ahead and plug in a 1. That was the question. And Daniel, question? At the last h, we plug in 0 for h because we're taking a limit as h goes to 0. So now plug in a 0. We got rid of it that way. So we end up with 2x. So this is the derivative at any given moment. If you want to know the derivative at 1, what should you do? Plug in 1 into the derivative. So find f prime of 1. In other words, 2 times 1 or 2. So this will be the slope of the tangent line at the point x equals 1. And finally, I have a part B to the question. I said, can you also find the equation of the tangent line at the point x equals to 1? The equation of the tangent line. So we have y equals x squared. We have at x equals to 1, we know y is 1 because 1 squared is 1, right? This is what the tangent line would look like, except that we're looking for the equation of the tangent line right now. Okay, let me give everybody a moment to copy the question, and then we'll discuss the solution. So find the equation of the tangent line at the given point, at x equals to 1. Exactly. We can use the point slope formula. The first thing to do is, at x equals to 1, determine what your y coordinate is. How do you determine the y coordinate normally? You would plug into the function. 1 squared is 1, so when x is 1, y is 1. So you have a point on the line. You know, this point is on the line. Do you know the slope of this line? The slope comes from the derivative, right? We did it up there at x equals to 1. What was the slope? 2. If you know a slope, and if you know a point, can you write the equation of that line? We should be able to, right? So let's summarize what we have. We have a point of 1, 1. And we have a slope of 2, which we got in the step above. All we have to do is now put it together. The rest is going to be algebra to write the equation of a line. But before I do that, are there any questions about what I have so far? Any questions? The y coordinate? Yes, how do you get the y coordinate? We plug 1, because x equals 1 was given to us, right? Plug it into the original function. That will give you y. So like f of 1 is going to be 1 squared, which is 1, correct? That is your y value. Exactly. Okay, so let's finish the equation of the line. So I'm going to use point slope form. You could use any other form as well. So y minus 1 equals the slope times x minus 1. And we just simplify. How can we check this? Can we graph the function and the line together on the calculator? We should be able to, right? You can do y1 is the function, y2 is the tangent line. Let's see if this equation really matches or looks like it's the tangent line. Let's check it out. Okay, so go to y equals and enter as your first function y equals x squared. As the second function, enter the line, which is supposed to be 2x minus 1, correct? Y equals 2x minus 1. And let's do zoom standard at first. Zoom 6 is going to give you a good range to look at least initially. So it looks pretty good there. You can zoom in further if you like to see if it's really tangent at the point 1. But this is satisfactory. If you got something completely weird, like your line is going opposite way or something, you know you did not get the right answer, you can go back and check your work, okay? So just to summarize a few things we've done so far. What does f prime of x represent? If I could find f prime of x for any given function, first of all, it's called the derivative of the function f, right? That's called the derivative. And what does it represent? There's a definition for it, right? The limit as h goes to 0. But what does it represent graphically if you find the f prime of x? Either the instantaneous velocity or I shouldn't even say velocity, instantaneous rate of change of the function, or you could say the slope of the tangent line, which are the same things, okay? Slope of the tangent line is the same exact thing as the instantaneous rate of change of the function at that moment. If we had a distance function, you would have instantaneous velocity. Okay, speaking of the velocity and distance function, okay, let me do something here. Clone the page and then erase. Okay, now we're going to revisit the example we did earlier because that was a very nice example. We had a good idea about what was happening, but we never confirmed our findings about what the exact answers. We had a pretty good idea what the velocity at the third second was going to be. It was going to be roughly negative 96, but we didn't know for sure. So would you please rewrite the example again on the top of your page? S of t equals, this was the function we worked with earlier, right? So we're revisiting the same example, but this time, we're not going to do numerical. We're going to do analytical. We're going to know once and for all what is the exact velocity at that moment. So S of t was negative 16t squared plus 500. Just to make it look more like what we've seen so far, I changed the t with the x. If you like, you can keep the t. You know, you can work with the variable t. No big deal. But just to make it look exactly like we have, I wrote it as negative 16x squared plus 500. And I rewrote for you the definition of the derivative of a function because we're going to apply it to this to find the instantaneous rate of change of this function. Okay. First thing I'm going to need to know is what is f of x plus h for this particular function s of x? What will be our basically in this case we're looking for s of x plus h, but that's just notation. So what will you get when you substitute x plus h into your function? You don't have to give me the simple answer. Just give me, you don't have to simplify it right away. Negative 16 times quantity x plus h squared, and then what? Plus 500. So would everybody agree with, was it Sandra? Would everybody agree with Sandra's suggestion for the first part? Okay, so all we did was go to the function, take the x out, plug in x plus h, right? Okay. Then we want minus what? Minus the function itself, which is, we're going with the x's, so we might as well just stick with the x's. So minus, in parentheses, negative 16 x squared plus 500. I'm going to distribute that negative in my next step. And everything should be divided by what? By h. Now we're going to simplify this. Just notice that every step of the way I'm carrying over my limit as h goes to 0 symbol. That's important because the moment I leave that out, I'm talking about averages, but I want instantaneous, so keep that in there. Now, let's do the work over here. What is x plus h quantity square? That's x squared plus 2xh plus h squared. Now, would you multiply each one of those with negative 16 and let me know what you're getting? Three terms, right? Starting with, good, negative 16x squared minus 32xh minus 16h squared. Let me pause for a moment, see if everybody agrees with Christine's suggestion so far. Okay, then what else should I be writing based on the line above? Plus 500. And let's distribute our negative sign. Plus 16x squared minus 500. Who lost two terms? You did? Okay. Right. Okay, so let's cancel out. The 16x squares will be canceled, and the 500s will be canceled. Excellent suggestion. We still have an h on the bottom, right? Now, if we plug in h right now in the remaining terms, we're going to have 0 over 0, which is indeterminate. To get rid of that, we're going to factor. We can take an h, but while we're at it, let me go ahead and take out a 16h. So what's left inside? Negative 2x, right? I took a positive 16. You could have taken negative 16 also if you wanted to. I took a positive 16h out. So I'm left with negative 2x and then minus h over h. So now the h's are gone. So let h go to 0 now, and what will you have? Let h go to 0. So this goes to 0 now, right? So what do we have left here? Negative 32x. Would everybody agree? Okay. Remember here, x is t, because instead of t, we're using the variable that we're more familiar with. So this is saying at any given moment, this is going to be the pattern for the instantaneous rate of change. So what is the instantaneous rate of change at the moment when time equals to 3 seconds? Plug in a 3 in there. Negative 96. So we were pretty close then, right? When we did our table, we were pretty close. But the good thing about this is it's not answering just what's happening at time equals 3 seconds. What if I want to know what is the velocity at the 5th second? Just plug in a 5 in here. You don't have to do another table of values. What about the velocity at the 10th second? Just plug in a 10 into this equation. So whatever, this gives you a pattern at any given moment, okay? So if I want to know what is the velocity at the moment 3 seconds, I'm going to plug in a 3 in there. And that will be negative 96 feet per second. That was the same exact thing as we had obtained earlier. But just know the power of this approach. If I want to know what is the velocity at the second, just plug in a 2 then. Then we also know the velocity at that moment. Negative 64 feet per second, etc. At any given moment in time, I can find the instantaneous velocity now using this one amazing formula. Yes, questions? Okay, the fact that the speed is negative, that indicates the object was moving downwards. Many of you are going to end up taking physics also, right? Because physics 1 with calculus 1, usually you finish calculus 1 and then you can take that class. When you take that class, if you do, you're going to learn that velocity is a vector. It has a magnitude, which is speed, and a direction. So in this case, the negative indicates the direction that it's going downwards. And then it's going downwards at a rate of, let's say, 96 feet per second. Because this was an object, if we look into the deep, what that equation represents, it was an object dropped from the top of a building, let's say, that was 500 feet. So its velocity basically is getting more and more. It's picking up more speed. Like at the second moment, the speed was 64. At the third moment, third second, it was 96. It's getting faster and faster as it's approaching the ground level, basically. Okay, let us take a look at one more example on applying the new definition of derivative that we have just seen. So the question is to find the derivative of this function and then to use that to find the slope of the tangent line at the point x equals to 0. And again, the slope of the tangent line basically is the same thing as finding the derivative or finding the instantaneous rate of change of a given function. So we need to begin by using that definition that we have just seen. I would suggest for my online students to pause the video here, try this problem by yourself, and then come back and take a look at the solution. Okay, beginning with the definition, which we are familiar by now. Again, f prime of x represents the derivative, and the right-hand side gives us the definition. Okay, so in the given function, everywhere we see an x, we're going to replace it by x plus h, so that we can write f of x plus h for this function. So we're going to take the x out and replace it with x plus h. And also don't forget to do it here. Take this x out and replace it with x plus h. So if we do so and apply the definition from the step above, we will get the following. Negative 2 times x plus h quantity square plus 3 times x plus h plus 1. So all of that is for f of x plus h. Then we want to subtract f of x. So I use parentheses there so that I don't forget to distribute the negative sign. So we subtract f of x. In the next step, we're going to expand all those parentheses, the binomials, etc. So if you do so, FOIL the x plus h square and distribute the negative 2 in, you will have the following. Of course, first write down that x plus h quantity square is x plus 2xh plus h squared. And then you can distribute the negative 2. So that will give you this part. Negative 2x squared minus 4xh minus h squared. Then you distribute your 3. That gives you this. Then you hit the plus 1. And don't forget, when you distribute the negative sign onto these, then you will have the last 3 terms. Okay. At this point, there will be simplifications. Let's see, what can we cancel out? The negative 2x squared with plus 2x squared, plus 3x with the minus 3x, plus 1 with the minus 1. And we will factor out an h. If we don't do that, we will have 0 over 0 at this point. So factor out an h. From the first term, you have negative 4x remaining. From the next one, negative h remaining. And from this one, a plus 3 remaining. So that gives us this line. On the bottom, we still have our h. Now we can cancel the h's as well. And finally, in the remaining expression, you can plug in 0 for h to take a limit as h goes to 0, and we are left with this answer. So once again, this represents the derivative at any point x. Since this question said, what is the slope of the tangent line at the point x equals to 0, we're going to need to plug in 0 into that derivative. So we have negative 4 times 0 plus 3, which is equal to 3. So this is the slope of the tangent line. If the question also asks what is the equation of the tangent line, then you will go one step further, find the corresponding y coordinate by plugging 0 into the function. You know the slope is 3, and you can use that information to get the equation of the line. For this one, we just wanted to find the slope or the instantaneous rate of change at x equals to 0, and that is our answer, 3. By the way, in the next section, things are going to get easier. We're going to derive what is called the shortcut rule. So just bear with me here with this section as we're doing everything by using the definition. But once we have the shortcut rules, we're going to do most of the problems that way. However, on the test, of course, I'll still have a few questions asking you to do the problem by using the definition, because I feel that it is important to understand where these shortcut rules are coming from.